Hello everyone, this is Dr. Zach wishing you a terrific day. For today's lesson, we're going to work on the direct comparison test. Before we begin the lesson, take a look at your lesson preview. 5 different tests have been presented. I want you to match the tests that you should apply to each one of these series or sequences and then determine whether or not they will converge or diverge. Get started. Your nth term test should actually be used with every single one of these problems because the nth term test is going to tell you whether or not your series or sequence diverges. Of course, if your limit as n goes to infinity of a sub n does equal 0, that indicates that your series or sequence could converge. In order to apply the geometric series test, you have to look for a very particular structure to your series. You must be able to indicate what r is equal to. Once you determine whether or not your series has an r value, you can easily see if your series converges or diverges. And then, once you know whether or not it converges or diverges, you could use this nice little formula in order to determine the value that your series will converge to. To apply the test for a telescoping series, it also has to have a very particular structure. Often, though, your series comes in the form of a rational expression. And if you look at question B, it can be rewritten so that it has the minus sign and the different components that are going to be added and subtracted for each term. P series, now those are fun. If you can recognize 1 over n to a p value, you can tell immediately if your series will converge or diverge depending on whether the p is greater than 1 or less than or equal to 1. So for this series, it sometimes comes a little bit disguised, and I'm hoping that you chose E for this P series test. The integral test, of course, takes a bit more work. When applying the integral test, you have to show that your a sub n, which is going to be equal to some sort of function f of x, is continuous, decreasing, and positive for all n greater than 0, because those 3 conditions are the only conditions for which the integral test can be applied. Now, the thing that you must also remember is you have to be able to find an integral very easily. So as you look at the questions A, B, C, D, and E, there are only 2 possibilities for which you could find an easy integral. And I think B, we already said, was telescoping, so A is probably going to be using the integral test. The test we're going to look at today is called the direct comparison test. So let's take a look at what we need to consider. We will have all positive terms because a sub n is going to be greater than 0, and we will also declare that b sub n is greater than or equal to a sub n. If the series with b sub n is converging, then the series with a sub n also converges. If the series with a sub n diverges, then the series with b sub n will also diverge. Now, I want you to convince yourself that this is true. Draw pictures to represent a sub n, b sub n in each of these and what they might look like when your series converges or when your series are going to diverge. So go ahead, draw pictures, and convince yourself that the direct comparison test is true. When applying the direct comparison test, we need to find a series to compare our problems to. So for example 1, let's write out a few of the terms to get a good sense of what is happening with our problem. So we'll have 1 plus 1 over 2 to the 2nd power plus 1 over 3 to the 3rd power plus 1 over 4 to the 4th power. All right, so I recognize a nice little pattern that is emerging. And I don't know if this is going to be convergent or divergent, but you want to get a sense of what's going to happen before you begin. Let's first compare our problem to, 1 and 1 and 1, just to see and understand what's happening. So if I think about the series that gives me the terms 1 plus 1 plus 1, that would be series k equals 1 to infinity of 1. And I know that this is divergent. So we're going to compare each of the terms. So we have 1 over n to the n is less than 1 or equal to each of the terms for our series. Now, with that in mind, notice that we know that the series involving the 1 is divergent. Unfortunately, that does not help us at all. So we need to come from a different approach. Let's again go back to our original. Let's see. Oh, this is 1 over 2 squared. And if I have 1 over 2 to the third power and 1 over 2 to the fourth power, and we continue as we go to infinity. Wait a minute. That first term that goes with this geometric series would be 1/2. And that series is k equals 1 to infinity, 1/2 to the nth or to the kth power. And I know this geometric series will converge because the r value is less than 1. When we write our comparison, we know that 0 is less than 1 over n to the nth power, which is less than or equal to 1/2 raised to the nth power for each term. But that's not actually true, is it? It's only good for n's greater than or equal to 2. But that's all right. We're not going to worry about what happens for the very first terms. Since we know that 1/2 to the nth power is a series that will converge, and that 1 over n to the nth power is smaller than this convergent series, from your squeezing theorem, we know that our series k equals 1 to infinity, 1 over k to the k power must also converge. Now, I said the squeezing theorem. So that's essentially the discussion I hope you had earlier, that the convergent series will squeeze our questionable series into converging. Let's take a look at example 2. Again, let's write our terms out so we get an idea of what's happening, some sort of sense. We have 1 over 3 squared plus 1 over 4 squared plus 1 over 5 squared. So do you see that it might be prudent to compare this series to a series k equals 1 to infinity, 1 over k squared? So if I were to rewrite this series just to compare what's going on, we have 1 plus 1 over 2 squared plus 1 over 3 squared plus, and then that would continue. Again, what we can see is this time for each one of our values, 1 over n plus 2 quantity squared is less than or equal to 1 over n squared, and this is for all n values. Now, go back and think for a moment. This is your p series, for p is equal to 2, so the series 1 over k squared will be convergent, and that tells us that since the larger series converges, the smaller series must also converge, and we know that the series k equals 1 to infinity, 1 over k plus 2 quantity squared must converge, and it must converge from the direct comparison test. Time to look at example 3. For example 3, we begin by writing out a few terms. We have square root of 2 over 1, square root of 3 over 2, square root of 4 over 3. So I see a lovely pattern, but I'm really not recognizing what's happening yet. So we're going to try something a little bit different. What if we were to consider the limit as n goes to infinity of root n over n minus 1? When we simplify, we would have the limit as n goes to infinity, 1 over square root of n. So our rational expression is very similar to 1 over square root of n. We recognize also that if we were to complete this limit, it's going to 0, and our series could converge, but I just don't know yet. Let's compare it to the series k equals 2 to infinity, 1 over k to the 1/2 power, so the square root of k. Now, what does this series do? It is divergent. How do we know? If we think about the p series again, the p value is going to be equal to 1/2, and if your p value is less than or equal to 1, your series will diverge. All right, let's set up our values and do a nice little comparison. For k equals 2, we have 1 over root 2, which is root 2 over 2. And then we will have 1 over root 3, which is root 3 over 3, and 1 over root 4, which is root 4 over 4. So conveniently, we can see that 1 over square root of n is going to be less than or equal to root n divided by n minus 1 for all n greater than or equal to 2. And these are each greater than 0. Therefore, from the direct comparison test, we can say that our series k equals 2 to infinity square root k over k minus 1 is divergent. For our next part of the lesson, we're going to mix all the different types of series so that you have to decide which test is most appropriate. So begin every question with your nth term test. If your series diverges, it's good to know immediately. Afterwards, look for structures. Geometric series, find the R value. Telescoping series are often disguised as rationals. Your P series, if we have 1 over n to the P, remember the P series is really convenient to use for your direct comparison test. Your integral test is best used if you can easily integrate your function. And then your direct comparison test is now a nice tool for you to use for the structures of problems that are non-standard. Go ahead and give this practice a great try. There will be a few problems that we'll discuss after you complete your practice. As you consider question 6, here's a reminder that the limit as x goes to 0, sine of x over x is equal to 1. See how that could apply to question 6 to determine whether your sequence will converge or diverge. Number 8, did you use your integral test? Make certain that you state all 3 components before you use that test. For question 9, please remember that n factorial grows way faster than 2 to the n. And lastly, number 10, the sine function will oscillate as n goes to infinity. How does that help you determine whether or not your series converges or diverges? For question 11, did you rewrite your problem using series notation? Because if you did, you may have recognized that you need to write this problem using partial fractions because it is a telescoping series. Number 13, you should probably rewrite this problem as well. It is a geometric series. Then let's take a look. Number 16, the algebra on this one is interesting. If we rewrite the problem as pi over n to the pi over 2, what can we say about this function? Is there anything you can compare it to? And number 17, this one is also a direct comparison test. If you were to consider what's happening to 1 over to the series n equals 1 to infinity, 1 over 4n. How might we better understand number 17? 18. You could rewrite this problem as a geometric series, and you could possibly even use an integral test. I think sometimes you have choices. Number 19, very similar to number 8, so give that a good try. And number 20, it is also harmonic, just as number 17 turned out to be harmonic. What do you know about harmonic series? At this point, I'm hoping that it is easier for you to determine which test to use. For 21, think about integration. I find 26 to be very interesting. If we were to drop the lower order terms, this most likely could be compared to a harmonic series. Make certain that you are always working with your nth term test as you begin each question. That's it. Have a great day.